Hi all. So we will begin with a pipe that has some radius, big R, and as we remember, the volume flow rate through the pipe will be equal to the conductance of the pipe times the pressure difference across it. Now, the real question that we have is, for a given pipe, can we actually calculate this G? So we look at a side view pipe, so just this right here. What we know is that we have a no slip condition at the edges, so that means at big R, so once you're at big R, the velocity is 0. So we know the velocity is 0 on all the edges. And then the simplest function it can be in between, parabola. So it doesn't quite look it here, but the biggest velocity will be in the center at little r equal to 0, so starting at center. Because in polar coordinates, r equals 0 is the center, and as you get further out, r gets bigger. So what we can say is that the velocity profile is going to be proportional to the radius of the pipe squared. And if we look at the volume flow rate of the pipe, it's going to be the area of the pipe times the velocity that it's moving in there. So we can say that this is going to be roughly the area, which is pi big R squared, because that's the area. And if we make an over assumption so that it's r squared everywhere, it's going to be roughly, it's still going to go as r squared, it's just going to be different by a constant, but at the center it's going to be big R squared. So then we're going to find that the volume flow rate is going to go as the radius of the pipe to the fourth. So a different video that you can look at is a derivation of Poiseuille's law that is in my YouTube videos. It'll show you how to do that entirely, but this is just to give you a conceptual idea. So the velocity profile, so the velocity at some point will be going as r squared, and the area also goes as r squared, so the volume flow rate will go as r to the fourth. And we find that the conductance of the pipe will be equal to pi r to the fourth. So this is what we had already said, and then there's some constants here. So 8, eta, and L. So L is just the length of the pipe. So as we make the pipe longer, the conductance drops. So as you make the pipe longer, it's harder to get water through there. And eta is the viscosity. So if you have something that flows really easily, like water, this is going to be a small number, and this is going to increase the conductance of the pipe. However, if you have something like honey or molasses that is very viscous, so it doesn't really want to move, then this is going to be a big number, and then the conductance will go down. So this more or less is Poiseuille's law, that the volume flow rate for a pipe is going to be equal to pi r to the fourth over 8 eta L. That was the pressure difference, and then this is the conductance of the pipe. So this is the full Poiseuille's law. What this really says is that a small change in the radius is going to have a dramatic effect on the conductance. There's one more thing that we can look at. So for things like blood, which is a living fluid, we have something that's Murray's law. So if we have a pipe junction, so what we have is blood coming in, and then it breaks off, it goes down there, down there. And this, we will say, has a radius rp. It's going to be the parent, and this will be a radius of rd1, so it's daughter 1, and this is rd2. What Murray's law says is that the cube of the parent radius is going to be equal to the sum of all the daughter radii. This is only for living fluids. So blood, and then this is also going to explain the pattern that you see in leaves for transporting liquids. So where this comes from is minimizing the amount of energy that is lost in terms of not just the dissipation due to the fact that you have some fluid resistance, but also the cost that it's going to take to keep producing new red blood cells and things of that nature. So it's the metabolic cost required to keep producing fluid.